Okay, so in the last video, I was giving quite a bit of background about proving that our two fields here are isomorphic, right? So we had these two fields. We had f3 of x divided by x to the third plus x plus 1. And then we had f3 of x divided by x to the third plus x minus 1. And in the last video, I was talking about how if we want to prove that these are isomorphic to each other, we want to start with the field on the left. This contains an element which is like x bar or alpha, right? And basically, the question with our isomorphism is where we want to send this alpha, right? And so in the last video, I talked a little bit about how wherever we send this alpha, it has to be sent to something that kind of looks like this, right? So a beta squared plus b beta plus c. And we figured out that this element of this other field has to have the same properties that alpha has. So in particular, like this equation here needs to be satisfied by this element, the a beta squared plus b beta plus c, because this is kind of the equivalent of the equation that we know alpha satisfies in this original field. So in this video, I'm going to go through actually solving this equation, and we'll see that there's multiple solutions for our coefficients for a, b, and c. Okay, so we want to solve this. The first thing that we want to notice that actually makes this easier than you might expect, right, is that we have this cubic term. And everything that we're dealing with here, right, so the a, the b, c coefficients, like these are living in f3 still, right? So normally when you're dealing with an expression like this, you want to like FOIL everything out first. The important thing to realize is that because the base field that we're dealing with is a characteristic 3 field, you basically don't need to do that, right? So we can actually just expand this as a to the third beta to the 6, right? So I'm just cubing this term here, and then plus b to the third beta to the third, and then plus c to the third. And that's it, right? And so I'm allowed to do this because I'm working over a field of characteristic 3. And so I can expand this term by just cubing everything on the inside. So then we want to think a little bit more about beta to the 6, right? If we go back here, so go back here. So what do we know about beta? Well, we know that beta to the third plus beta minus 1 is equal to 0, right? And so we can use that to say the following, right? So we can subtract the beta plus 1 to the other side. And then if we want to know an expression for beta to the 6, right, we can just square both sides of this, right? On the left, that'll give me beta to the 6. And then on the right, what will I have? So I have 1 minus beta squared. So that's going to be beta squared minus 2 beta plus 1. So that gives me kind of an expression here for beta to the third, and also gives me an expression for beta to the 6. So if I come back here now, I have a new way of writing this guy, right? So I can write this as a to the third. We just figured out beta to the 6 is actually beta squared minus 2 beta plus 1. Okay, and then we figured out that beta to the third, that one was easier, right? That was just 1 minus beta, and then c to the third. And so this is a way of writing like this expression here, but we're sort of only using like first or second powers of beta, right? So then that's nice because now I can take my equation up here that I was that I was referencing before, right? And what's a way that I can rewrite this that just has lower powers of beta now? So this is a to the third to beta plus 1, and then plus b to the third 1 minus beta plus c to the third. And then we had an a times beta squared plus b beta plus c, and then plus 1. So this part is really just solving an algebraic expression. But if we compare our coefficients, right, because, remember, we're still basically working with polynomials, so we can kind of compare the coefficients of like the beta squared and like the beta. So we can look at like this beta squared here. And if we do that, we get that, we have a to the third beta squared and then plus a beta squared. So our coefficients, I'll just kind of group together the coefficients here. So we have a to the third plus a beta squared. Then what are my coefficients on the beta? Well, it looks like I have negative 2 a to the third. I have this beta here, so that'll give me minus b to the third. And then I have plus b over here, beta. And then for my constants, so what do I have there? So I have a to the third plus b to the third plus c to the third plus c plus 1. And all of that is equal to 0. Okay, so what does this tell me? So again, you want to think about this as we're kind of like comparing coefficients, right? So on this side, we basically have 0 beta squared plus 0 beta plus 0. And so that tells me the following. So I know that this coefficient, so this a to the third plus a is 0. I know that this expression here, so negative 2a to the third minus b to the third plus b is 0. And then I know that this entire expression here is 0, right? So just write that down. So I have these three equations, and I have all of these being equal to 0. And remember, right, so as we kind of explained before, that all of these guys live in F3, right? So like these are all elements of F3. And so all of these are basically just going to be 0. All of these, like the A, B, and C, are going to be equal to 0, 1, or 2, right? So using that, you can kind of check. If I think about like this equation here, I'm basically saying I have an element of F3. If I raise it to the third power and then I add the elements again, I get 0. And you can kind of check through the different elements of F3, and you'll find that the only thing that actually works is if A is equal to 0. So that actually solves for A. If I look at this equation now, using the fact that A is 0, I get B equals B to the third, right? That's equivalent to this equation that I started with. And there are actually 3 solutions to that, as you can check, right? So try plugging B into, or try plugging all of these numbers into this expression and then reduce them modulo 3, and you'll find that all of those numbers work. And then I won't give you the full details of this, but depending on which value of B you choose, when you substitute into this last equation, you'll get different solutions for C, right? So the solutions that you end up getting are, so let's see if I can remember. So if B is equal to 0, I think that tells us that C needs to be equal to 1. So then that means that alpha is being mapped to 1. If B is equal to 1, then C is going to be mapped to 0. So that just gives us beta. And then if B is 2, then C is equal to 1. Okay, so these are the solutions of the equation. And I think I'll wrap this video up here. And then in the last video, I will explain what the isomorphisms are.